Hi, I'd like to take a look at another line integral today. It's been a couple other videos practicing these kinds of things. This one's special because when you look at the curve C, you'll notice that the curve C consists of the line segments, so that's plural. And I'll underline the first one in red. The first line segment goes from 0, 0 to 2, 0. And then it's the second line segment that goes from 2, 0 to 3, 2. So another little special thing to keep in mind when looking at this, you'll notice that this has this line has a dx in it and a dy in it. So there's no ds. Just be careful when you plug in for dx and dy. But we'll need our parameterization first. And also, since we have two line segments here, we're going to need two integrals that will need to be added together. So first things first, let's draw a picture of our curve C, and let's also try and find the parameterizations. So in the first case, let's draw the line segment. Here they are. Here's x, y. The first line segment, if we look at it, is underlined in red here. We're going from 0, 0 to 2, 0. So I'll start here at 0, 0 and go over to the point 2, 0. And it turns out this is a pretty easy line segment to parameterize. What can we say? Well, x clearly varies from 0 to 2, so I'm going to let x equal t. And y is always 0 while you're on this curve. And then additionally, we can say something like t is between 2 and 0 the whole time. And so now we've found the parameterization for just the first line segment. I'm going to call that C sub 1, like the first little subset of the bigger curve C. And if we go back here and we look at what was underlined in blue, we have a second line segment that is going from the point 2, 0 to the point 3, 2. So we go back here, we start at 2, 0. That sort of picks up where it left off. That's good. And it goes over to x equals 3, but up 2 units. So maybe something like this to the point 3, 2. So while I called the first little piece C1, I'm going to call this one C2. Now, what I need to do is find the equation of this line. And then after finding the equation of this line, I can write it in parameterized form. So there's a couple ways you can do that. I'm going to do this sort of like a classic way. My favorite equation of a line, or form of a line, I should say, is y equals m times x minus x1 plus y1. This is sometimes referred to as the point slope form of a line. I know I want this line to go through either the point 2, 0, which I see down here, or the point 3, 2. I'm going to use 3, 2, so I'm going to say y equals, I'll leave the slope blank for now because I'm going to go find that, x minus 3, and then plus 2. So that's why I like this point slope form. You can literally just plug in the point that you have. Okay, I need the slope of this little line segment. We can do it just by inspection if we want. We can see that we've gone over 1 in the x direction, and because we went from x equals 2 to x equals 3, and then we've gone up 2 in the y direction. You can see we've gone from 0 to 2. So slopes in general, right, when we write them, our slopes, m I'll call it, is a change in y over a change in x. In this case, we have that change in y of 2 and the change of x in 1. So if we simplify that, we just get 2. So there it is. There's the equation of that line. There's other ways to do it. Maybe you saw something more efficient. And like I said in other videos, it's easier, or I should say it's easy to parameterize a function whenever you have y equals all by itself here. So we have y equals all by itself here. So how do you do that? When you want to parameterize it, you just let x equal t, and you let y equal 2 times, and you make it t minus 3 plus 2. It's easy to tell here, that's a 2 there just in case. It's easy to tell here that x would just go in for t, and you'd have the line that's up above. Okay? And then finally, we want to make sure that we use the correct values of t. So we want to plug in numbers so that we would start at the point x is 2, y is 0. So it looks like we would have to have t be bounded from below by 2 and bounded from above by 3, because that's where this line segment exists. I always get a little nervous when I do these. I always just double check my endpoints and my parameterization. So if I were to plug 2 into that line segment there, you can see that you would have, let's just write this out just so we're clear. We'd have y equals 2 times 2 minus 3 plus 2, or y equals 2 times negative 1 plus 2, or 0. And that's exactly what we wanted, because we wanted to be starting at the point 2, 0. All right, let's plug in the value of 3 for t. So y will be 2 times 3 minus 3 plus 2, or we get y equals 2 times 0 plus 2, or y equals 2. And that's a good thing also, because the other point we wanted to go through, you can see it up here, let me just circle it, was the point 3, 2. Okay, so now we have two parameterizations. Let's write this out a little bit more cleanly, keep ourselves organized. So the first curve I called C1, x was just equal to t, y was always equal to 0, and this constriction for t was from 0 to 2. The second curve, C1, or C2 we'll call it, sorry, we just found that. X was again equal to t, but y was equal to 2 times t minus 3 plus 2, and that domain was from 2 less than or equal to t and less than or equal to 3. So there you have it. And ultimately, sometimes you'll see in some textbooks, I'll just familiarize you with this notation. They'll say C equals the union of C1 and C2. So this symbol in the middle here is union from set theory. So if you see that, don't be surprised. It just means that the curve C is these two line segments put together. All right, so let's not lose track of everything. It took us a while to parameterize, but our goal here is to find the value of this integral. And we're going to find the value of this integral using this parameterization. So what you're going to need to do is two integrals. You're going to do one integral for the curve C1 and a second integral for the curve C2. So that's what we need to do here. All right, so let's take a look. Let's go to a new page here. So we have the first integral. I'm going to go from 0 to 2. It's xy dx plus x minus y dy. And let's not lose track of it. For the first curve for C1, you can see that x is t and y is 0. Just look at the top there. And you can see my bound 0 to 2 that I used already. So everywhere there's an x, I'm going to put a t, and everywhere there's a y, I'm going to put a 0. So this is going to be integral 0 to 2 t times 0 times dx. And actually dx here, if you think about it, the derivative of x, if x is equal to t, is just 1. So I can erase dx here. Well, I could put, well, it's really 1 dt is what it is. And I'll put plus x minus y, so that's going to be t minus 0 dy. Now in this case, y is equal to 0. So if I were to take dy dt, I would get 0 dt times 0 dt. So what happens here? Well, this whole thing collapses to 0, or just that product, yep. And then this thing too collapses to 0. And therefore, you're integrating from 0 to 2, 0 dt, which is just 0. So nothing happened there. Okay, so we didn't have any, either the net area is 0 or something like that. That's probably what happens. Okay, that's one part of it. So we have to go back now. We need to do an integral again using the second parameterization. So I'm just looking at this now. I'm looking at, I'll underline it here. I'll circle it. looking at this piece here and I'm thinking, you know, I should have taken the time to simplify that. So let's just do that on another. We'll do that real quick. So if I were to simplify that, I get y equals 2t minus 6 plus 2, or y equals 2t minus 4. So that is the equation of that line in a simpler form. All right, so let's go look at this. X is equal to t, y is equal to 2t minus 4. 2 is less than or equal to t is less than or equal to 3. And we're integrating integral xy dx plus x minus y dy. So integral x is t, y is 2t minus 4, and then dx is the derivative of x, so that's just going to be 1 dt. All right, interesting. Oh, let's put our limits here. It's going to go from 2 to 3. That comes from our domain up top. Right, that's where that's coming from. And then we're going to have plus x minus y. That's going to be t minus the entire expression y. So be careful with that. I'm going to underline this here in red. This whole thing I'm underlining in red is going to be subtracted. So it's going to be minus open parenthesis, and in here, let's color code it, the 2t minus 4. That's a 4 there. Okay, great. And then we'll close parenthesis. And then it says dy. Well, the derivative of the y term here, that's that thing underlined in red, the derivative of 2t minus 4 is 2 dt. So I'll have a 2 and a dt here. Okay. So this isn't too bad. We just got to slowly and be careful with all our distributing and exponents. This is where mistakes are easy to make. So if I distribute here, I get 2t squared minus 4t. And plus over here, I've got a 2 I can distribute plus a negative, so let's be a little careful. I get t minus 2t plus 4 all times 2. So it's negative t plus 4 times 2. And so when it's all said and done, I get negative 2t plus 8 dt. So that's where this part of the expression came from. Integral from 2 to 3. Let's see, anything that can go together? Looks that way. So we did integral 2 to 3, 2t squared minus 6t plus 8 dt. And now you're in a very basic Calc 1 problem. Let's finish this off. Antiderivative here, 2/3 t cubed minus 6t squared over 2. I could have just made that 3t squared. That would have been easier. And then plus 8t. And then we got to evaluate this thing from 2 to 3. Okay. So we take the time and we plug in 2 first. Let's see, I'll plug in 3 first, that is. Sorry, right? We always take this first number, plug it into the expression, and then we plug in the bottom number and subtract. We plug in 3. 3 cubed is 27 times 2 is 54 thirds, right? And then we're going to have minus, this 6/2 is really a 3. If I plug a 3 in there, I'm getting a 3 squared is 9 times 3 is 27. And then lastly, I'm going to plus 8 times 3, which is 24. And then minus, if I plug in 2, 2 cubed is 8 times 2 is 16, so 16 thirds. And then if I plug 2 in here, 2 squared is 4 times 3 is minus 12. And then if I plug the 2 in the last part, I get 16. Okay, so I think I'll save you some time if you just take the time to type all this in. What you'll end up with is, I'm getting 17 thirds. Okay, which actually turns out to be the final answer to the problem, because don't forget, we did another integral a moment ago, but when everything's said and done, we just got 0. And you're going to want to add these two integrals together, but 0 plus 17 thirds is just 17 thirds. So the answer to this problem turns out to be just that. Okay, great. Thanks for watching.